Hello again, Advanced Calc. We're doing 7.3 here. The ice sheet says 4, 5, 7, 10, 12. 4 is kind of gross. We're going to stick with 5, 7, 10, 12. These are a bit more fun in the sense that they're kind of like cute applications of the fundamental theorem rather than grindy epsilon proof things. So 5, I think the answer's in the back. I'm going to just do, maybe I should do all these. I think you guys have to do number 6, right, which are applications of the fundamental theorem. So let me show you the basics here. So A is the most basic case where you have 0 to x, 1 plus t squared dt. You got some sort of function with an x on the edge, and you're trying to take the derivative. So this is big F of x. So f prime is the general trick. The theorem tells you just plug in x down here. That's how you take a derivative when it's a function, when it's a constant f to x. B, however, is more complicated. This time the integral goes from minus x to x, and so that doesn't quite fit the formula of the theorem. So what we're going to do instead is we're going to split this function up. 0 is in between minus x and x. So I can use integration properties to write these as two different integrals. And now there's a couple ways you can approach it from here. Probably the simplest thing to do would be to do this one. So if you're going to take the derivative, this would be root 1 plus x squared. And then you can see that this is an integral that's even and symmetric, so it should just double. So this one should also be 1 plus x squared. So you get double. If you don't believe that, then here's an alternate route. If you take that, well, after I split it, you take the first one and you flip it upside down, which makes it negative. You go 0 to minus x, 1 plus t squared. And this one, nothing changes. So let's go ahead and say we integrated that. That's the same trick. Nothing changes there. Okay, now this time you do this integral, you've got x. What you do, though, this is setting up for the next problem. Anytime you have something here, you put exactly that there. So negative, and then 1 plus negative x squared. But you also have a chain rule. This is not x, this is negative x. You're taking a derivative. The derivative of that is minus 1. And then here's the other stuff. These two negatives cancel. When you square a negative, you get the original, so you get what I had before, the same thing twice. Okay, so this chain rule thing is a little strange. That's also what you do for C, so let's do that again. C is cosine t squared dt, but you're integrating from 0 to sine x. And the rule is, you have a constant to the x, whatever's in here goes there. That should be x normally, but it's not, so we use the chain rule. So you put exactly what's up there. So this would be sine x quantity squared. And then the chain rule is not this mess, it's the chain rule of what you had in the top of the integral, where the x was. That should be a cosine x, because it's the derivative of sine of x. And then D is the craziest one. You're going from x squared to x cubed. F of x goes here. And then we're back to the square root 1 plus t squared. Notice what's in the integral really doesn't matter that much. So I don't necessarily know which one's big, x cubed or x squared, but I know I need constants at the bottom. And it doesn't really matter what the constant is. But if you think about just using 0, and then subtract 0 to x squared. These might have both gone farther than they needed to go, but they would, the extra area on each one would cancel when you subtract. So I'm thinking about this if like this is A to C and this is B to C. You take the difference. Hold on. Let me say that again. A to C, A to B. Take the difference. What you get is B to C. So I'm using the integration facts here, not really any thing about derivatives. Okay, so now when you take the derivative, you're going to use the chain rule on both. So you're going to have x cubed squared times 3x squared and then minus x squared times 2x. Should probably make those x to the 6th and x to the 4th. Okay, and there's your crazy derivative after all that. And then number 6 is similar kind of tricks. But just some nice applications here. Okay, so 7. Now you need to do this again, but you have a new function. You have, and it says be careful. 0 to x, x e to the t squared. And it says find the derivative, and x is in 0, 1, if that matters. And the hint says do not just make it x e to the x squared. It also says find for the first derivative, but it says find the second derivative. Okay. Notice that there's an x here. That's different. Normally those are all t's. That's where you can easily get confused. So I'm actually going to pull that x out because it's a dt integral. So the integral doesn't care about x's inside. Okay, now when I do the derivative, I do the product rule. So x becomes 1. This stays the mess that it is. And then over here you get x times e to the x squared. Now when you take the second derivative, the first term becomes e to the x squared now. The second term requires the product rule. It's 1, and then the chain rule gives you this. So when you're all done, you have, I think, 2x squared plus 2, 1, 2, and then 2x squared times e to the x squared. So that whole problem is really just about the hint, the trick, and then you're doing the same stuff we did before. You're just being careful with the product rule and with the variables. It's not clear to me why they made that condition and worried about where x lived, but in any case, that's the formula you should get. Alright, so now we're jumping to number 10. It says use the theorem to find a limit. It's the limit as x goes to 0, 1 over x, and then 0 to x, square root 9 plus t squared. Okay, so my first impulse is actually to use L'Hopital's rule. But they say use the definition. I'll show you both ways. So using the way that they wanted to look with the definition, you know that the derivative of this thing, if that's f of x, you know f prime of x is square root 9 plus x squared. So I'm going to think about that as f of x. You can actually make this kind of a derivative definition. Think of that top integral as f of x minus f of 0. Notice if you put in 0 for x, an integral from 0 to 0 would be nothing, right? It would go away. And then the bottom is x minus 0. Now you've got the derivative definition, which is this, and then you get this answer. So you just convert it into the definition of derivative. That's one answer. My go-to, rather than looking to make that perfect little expression for f prime, I would lean towards L'Hopital's rule since we've proved that. So if you have this, and you know from the theorem that this part is differentiable, t squared over x, so you get, when you plug in 0, you get 0 over 0, so L'Hopital's rule applies. The bottom becomes 1, and the top becomes 9 plus x squared. And so you get 3 here. I didn't finish up here, did I? This is not f prime of x. This is f prime of 0. Right, I plugged in 0. So that should be 3. In either case, you should get 3. I think this is much easier. Okay, one more. So this is number 12. And they say basically the integral from a to x is the integral from x to b. So f is continuous, which means it's integrable. And they say if you go from a to x, f of x, you get the same thing as from x to b. And they want you to prove that f of x is 0 everywhere. Okay, well, if you use that theorem that we've been using, think of big f of x as the integral from a to x f of t dt. Right? Inside the, it's a dummy variable, right? In fact, I kind of goofed up earlier. I shouldn't have x here and here. They just write f. I'm going to use t where they just write f, but I should not use x inside and outside. That's a rookie mistake, Dr. T. Okay, so if we call that big f of x, well then f prime is just f of x, but this is supposed to be equal to x to the b f of t dt. And so if you do it this way and you flip it upside down, negative x to b f of t dt, and you take this derivative, you get f. See, I forgot when I flip it over, I don't put a negative here, do I? I put a negative right here, excuse me. So here, then you get f of x, but you get a negative out front. So if this is equal, you get f of x is equal to negative f of x for all x. Well, the only number that's equal to its negative is 0. So that means f of x is 0 for all x in a to b. All right, that is the end of chapter 7. We did it.